Earlier, we talked about pressure in a liquid, and now we're going to talk about pressure under a whole bunch of gas. And just like with swimming to the bottom of a swimming pool, you feel pressure due to the weight of all that water above you. When we're at the bottom of our atmosphere, like on the ground, we feel pressure due to the weight of all that air above us. And one interesting thing to note is that from the ground to the top of our atmosphere is roughly 40 kilometers. And it is not the same density at the top as it is at the bottom. It starts out at a large density and gets less and less and less and less and just kind of wisps off to nothing. But, if you go 40 kilometers down the road, you're in the next town. But if you go 40 kilometers straight up, you're in outer space. So in order to find the weight of all that atmosphere, we need to find out what the density is of a certain volume of air. And one experiment that you can do is take this flask here that has a valve at the top, push that button which opens the valve, and the air that is in your classroom or the room you're in will equalize in pressure so that the air in here is under the same pressure as the air in your classroom. And then you just weigh the container with air. And then you hook it up to a vacuum pump and pump out all the air, and getting rid of the air gets rid of some mass. And you have less mass here, so you just subtract those, and you get about 1 gram. Now, I need to say that I'm doing this experiment in Denver, Colorado, and everybody who visits Denver realizes that the air here is less dense. It really is less dense, and it is quite measurable. If you were to do this same experiment in sea level somewhere, we would find that it was about 1.29 kilograms difference with air in it versus air out. Now, back to the number here for Denver, 1.0 grams, that was for 1,000 milliliters or 1 gram per liter. And if you convert that into cubic meters, it's going to be 1,000 liters in a cubic meter. So it'd be 1,000 grams or 1 kilogram per cubic meter. Again, that's the density of air in the Denver area, about a mile off the ground. Now, this is a container of water that is 1 meter by 1 meter by 1 meter. And we might remember earlier that if this is water, it has a density of 1,000 kilograms per cubic meter. But if you were to take out the water and just find the weight of the air in that container in 1 cubic meter, it's going to be 1.29 kilograms of air. So the density of air at sea level is 1.29 kilograms per cubic meter. If this was in Denver, it would only be about 1 kilogram per cubic meter. But to put that in perspective, and just to appreciate just how heavy air really is, 1.29 kilograms, if you have a mass set here, it's a full 1,000 grams, 1 kilogram, another 250 and 220s make 1,290 grams, or 1.29 kilograms. One thing to note also is that the density of air varies dramatically. If the air is warmer, it's going to be less dense. If there is more water vapor, if it's humid, it's going to be more dense. And if you go up in elevation, it's going to be less dense. So this number here is what you would typically find on your average day at sea level, at 0 degrees Celsius and at sea level, and it's dry air. If it's warmer, like about 15 degrees Celsius, it's maybe about 1.2 kilograms per cubic meter. All right. Now, just like we did with liquids, you can find the pressure under all that air. Pressure equals density times gravity times height. And turns out that does not work. You cannot use this equation for measuring the pressure under this ocean of air called our atmosphere. The reason being is when we had this for liquids, the density of that liquid was the same at the surface as it was deeper down. But it doesn't work because gases are compressible, that the density changes low down versus high up. Okay, the density is not the same at all depths. And if you were to look at a chart of the altitude in kilometers and the density, there's that 1.22 kilograms per cubic meter. That was if it was 15 degrees Celsius at sea level. And earlier I said it was 1.29 kilograms per cubic meter. That's if it's at 0 degrees Celsius. But very dense at sea level, and 10 kilometers up to drop down to this, and all the way to the top of the atmosphere. Earlier I said that about 40 kilometers was the top of our atmosphere, and here I go all the way up to 50. But the point is, the top of our atmosphere is not a definitive spot. It just kind of wisps off to nothing. But by about 40 kilometers, there's not a lot of air up there. And so what we want to do in order to find the weight of the atmosphere, the pressures due to the weight of all that stuff above us, we have to figure out what all that stuff weighs, or the mass of it as well. Now, if I had a 1 cubic meter box right at sea level, 1 meter by 1 meter by 1 meter, and it was at 0 degrees Celsius at sea level and dry air, it would be about 1.29 kilograms per cubic meter. But that's not all the air in the atmosphere. We have to stack on top of that another cubic meter. And because it's higher in the atmosphere, it's going to be a little less dense. And you stack more and more and more and more and more and more and more. Now, I've only shown 1, 2, 3, 4, 5, 6, 7. So we're 7 meters off the beach. And if we were to continue stacking cubic meters all the way up, 40,000 cubic meters, the very bottom one's going to be 1.29 kilograms, and it gets less and less and less. At the top here, even go another 10 kilometers up, the top one's going to have very, 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 very little mass. But if you add up the weight of all those cubes, the weight bearing down on 1 square meter would be the pressure. The weight of all that stuff onto 1 square meter is the pressure that would be at sea level. So here we have 10 kilometers all the way up to 40 kilometers. If we had a column of air 1 meter by 1 meter by 40 kilometers, it would weigh about 11.2 tons. So we have 11.2 tons weighing down on 1 square meter. In the Denver area, it's only going to be about 9.37 tons per cubic meter because we're missing the bottom mile of air. The tallest mountain in Colorado is Mount Elbert, 14,433 feet. And the weight from there all the way up is only about 6.83 tons, weighing down on 1 square meter. The tallest mountain in the world is Chumilongma, also known as Mount Everest. And these pictures are to scale here, but it only weighs about a third of what it does at sea level. From there up, only weighs about a third as much. Now, if we were to do that in metric units, in MKS units, we would get newtons per square meter. I'm only showing 3 sig figs here. A lot of times you see it as 101,300 newtons per square meter. That's typical atmospheric pressure at sea level. In Denver, Mount Elbert, and Everest. And then if we were to do that in imperial units, we would get how many pounds there were per square inch. So if this column was not 1 meter by 1 meter, but rather 1 inch by 1 inch, the weight all above that 1 square inch, about 14.7 pounds on a typical day. 12.3 in Denver, 9.0 on top of Elbert, and only about 4.9 pounds per square inch on the top of Everest. If you're going to remember some numbers, maybe this one would be a good number to remember. It's the metric unit, or the MKS one, and this is the imperial unit for atmospheric pressure. One thing we did not talk about when we were talking about liquid pressure is we did talk about that rho GH, density times gravity times height, can calculate the weight of that. But we also now have to stack on top of that the weight of the atmosphere. So if you're down here, not only do you feel the weight of the water bearing down on you, you are also feeling the weight of the atmosphere. So we call that P sub naught, or the initial pressure, which is the atmospheric pressure that we initially feel just before we jump into the water. So the pressure down here is that atmospheric pressure plus the pressure due to the liquid. That is called absolute pressure, which is just the total amount of pressure. Gauge pressure is just how much more pressure you feel than the atmosphere. So if we had a pressure gauge right here, not in the water, the pressure gauge would read 0 if it's a gauge, because it's not measuring the atmospheric pressure. It's just because that's just your baseline. Gauges only measure how much more pressure there is than the atmosphere. So here's a tire pressure gauge, and it's pushed up against the valve stem of the tire, and it's reading 32 psi. So what is the pressure inside the tire? Well, it's not 32 psi. 32 psi is only how much more pressure there is in the tire than there is outside the tire. Okay, and if you were to completely deflate that tire, like totally let the air out of it completely, the gauge would read 0, but there's still atmospheric pressure inside the tire. So the gauge pressure, also known as relative pressure, is how different the pressure is inside the tire versus out. If the gauge reads 0, there is no difference in pressure inside the tire versus outside. But the absolute pressure is what the gauge reads plus how much pressure there is in the atmosphere. So if the gauge reads 32 psi, there's still atmospheric pressure there. So you add those two, that's the total pressure inside the tire. And atmospheric pressure is phenomenal. It's really an amazing amount of weight bearing down onto an area. If you had steam inside, like if you're going to get inside this thing and clean it out with a steam cleaner, and if you get out and close the hatch, the steam will cool and condense, the pressure will drop, and the atmosphere can actually crush this big oil tanker. And here's a video of it. There's a hose here taking the air out of it, but it's quite frightening, and you would not want to be in there because the weight of that atmosphere is phenomenal. One interesting note is that a rope is really good at pulling things, but you wouldn't use that rope to push. It would become limp and couldn't push. Similarly, air can push against things, but air cannot pull. And the reason air can push is because it's individual molecules colliding against the surface of something that's pushing against it. But air cannot pull. And the layman's term for air pulling is to suck. There's no such thing as suction. So when you see these things, people who aren't familiar with science would call those suction cups, but we call them atmospheric pressure cups because these are not sucked against the surface. You're just decreasing the pressure on the outside, and the atmosphere is pushing them against the surface. A guy by the name of Otto von Guericke lived in Magdeburg, Germany, and he researched the physics of vacuums. And he had these big spheres here with a seam here, took out the air in between, could not get these teams of horses to pull those things apart because with a vacuum in there, that air pressure is pushing those with a large amount of force. So if this is half of a sphere and half of a sphere, and you put those two things together, take out the air from the inside with a vacuum pump, the atmosphere is pushing all the way around. And it's always perpendicular to the surface because, back to that molecular theory, that molecules colliding into that surface can only push perpendicular to it. If the molecule collides at an angle, it's only the perpendicular component that's putting a force on it. Well, all of those forces have components that are horizontal and vertical. And once we draw the components, you get rid of the actual vector. And we're looking at to see how much force is holding that sphere together. So how much is pushing left and how much is pushing right. So we're going to get rid of those. We're going to squash those forces all up into the cross-sectional area. And one thing we see is that there's more force toward the center, less force toward the edges, because these only have small components. But these forces are closer together and they're further apart here. And it does work out that the force, since pressure is force divided by area, force is going to be pressure times this cross-sectional area. So if I had these two things and it was 5 inches in radius, in diameter, only 2.5 inches in radius, we can find the cross-sectional area of that by pi r squared. So about 19.6 square inches is the area. And we count about 19.6 full square inches on that 2.5 inch radius. Well, on each square inch, on this little square inch at sea level, there'd be about 14.7 pounds of force. And on that one, and that one, and that one, on all 19.6 of them. So the total amount of force holding those two things together, just due to the atmosphere, would be close to 300 pounds. It's amazing. You could take a glass of water, fill it up to the brim here, take a piece of paper and set it on top here. Now the atmosphere is weighing down. Molecules of air are colliding against that surface of the paper. And the water molecules are moving around and they're colliding against that surface of the paper. So atmosphere is weighing down, but even if we flip that upside down, those molecules are banging in every direction. So the atmosphere is also pushing against the bottom of this because the molecules are moving in every direction. And the weight of the water in that container is far less than the weight of the atmosphere all the way up to the top. So the piece of paper doesn't come off as long as it makes a good seal. If you're going to try this, maybe try it over the sink so you don't make a mess. All right, let's see how we measure atmospheric pressure. Or just the pressure of a gas. So if we had a balloon here and we had a straw sealed onto it, put our finger here, air doesn't come out, but we would like to measure the pressure in that balloon. And remember, pressure equals rho GH does not work for air because its density is different at every depth. We cannot use that We cannot use that equation for air, so we're going to use that equation for air. But we're going to set up an apparatus where it does work. If we had a graduated cylinder like this and we had it filled with water and we put this thing under that water, we dip that straw into there, water is going to start to come up on the inside of that straw. And there's going to be a point where there's a boundary between water and in the straw and air. And right at that boundary, the air pressure pushing against the water is balanced by the water pushing against the air. So right at that spot there, the pressure in the balloon equals the pressure under that much water. We can't use that equation to find the pressure in a gas, but we can set up an apparatus to find the pressure in the water, which is the same as the pressure in the gas. So if we were to pull that straw up past that point, air is going to start to come out. There wasn't enough pressure to hold the air in. But if I measure it, it's about 15 centimeters, 0.15 meters. So We can measure the pressure of the air inside here by measuring the pressure under the gas. The density of water, 1,000 kilograms per cubic meter, the acceleration of gravity, and how deep we are, we find that there's about 1,470 newtons per square meter, or 1,470 pascals of air pressure in there. And a guy by the name of Evangelista Torricelli was the first person to set up what's called a Mercury Barometer. And he literally used mercury, big tub of mercury here and a large test tube here. And he set up this apparatus to find the pressure in the atmosphere by finding the pressure under a certain amount of mercury that had the same pressure as the pressure of the atmosphere. So let's say we have this big tub of mercury, long test tube here that is open on the top, closed on the bottom here, and we fill that thing with mercury all the way to the top here, so there is nothing but mercury in that tube. Take your finger, probably a good idea to wear a glove, hold it over the top, flip the whole works around, lift that end up and into the mercury, pull your finger away, and the mercury will start to drain out. But if there was mercury up against the glass there and it just pulled away, what's inside there? Well, it's not air, it's a vacuum. If we were to drill a hole into there and let atmospheric air go into there, when we pull the drill out, it would drain down. Here's why. The atmosphere weighing down on this surface and the atmosphere coming through the hole and weighing down onto the surface inside there, the mercury is going to be at the same depth. If we were to take a vacuum hose and put over there and then turn that back into a vacuum, it doesn't suck up. Remember, there's no such thing as suction. It's the atmosphere out here pushing down on the surface that's pushing that mercury up to the top there. And it is a vacuum on top of there. So what we have is, if this is a mercury barometer, and we'll shrink it down a little closer to scale, although it's not 10 kilometers tall, here we have mercury in the deep. If we go this deep under mercury with a vacuum sitting on top of that mercury, it's balanced by the pressure here, but this mercury doesn't have a vacuum on top of it. It has all this air on top of it. And on top of the air is a vacuum. Okay, so if we were to put that whole thing in a big bell jar and take out atmospheric pressure that's pushing against that surface, and so that's a vacuum in here, well, a vacuum in here and a vacuum right there would bring those two surfaces back to the same level. So if we set up this apparatus, we would find that typically at sea level, it would be about 760 millimeters, 0.76 meters, or 29.92 inches, which, let me just say this again, it's so important. This mercury here is exposed to the atmosphere. So the pressure of the atmosphere pressing down on this is the same as the pressure under that much mercury with nothing on top. Well, we can calculate the density, the pressure. Pressure gets greater and greater and greater linearly. But the pressure right here in the mercury is the same as the pressure under that atmosphere. The density of mercury is crazy. It's about 14 or 13.5 times as much as water. But if we take density times gravity times height, density times gravity times this typical depth, we get that number for atmospheric pressure, 101,000 newtons per square meter, and that's just showing 3 sig figs. So here we have a mercury barometer. There's that mercury exposed to the atmosphere, and then a tube here and a way to measure it. So this container here does not have the lip of that container right here. This glass curves around like this and goes all the way to the top here so you don't accidentally spill it. There is a rubber stopper on there that you can push down so that you could lay it on its side and it doesn't leak out. You just have to remember to release that rubber stopper to allow the atmospheric pressure to push against there. But here's in our thing here, we get 62.5, which is a lot less than 760 millimeters. This is 62.5 centimeters, so 620 millimeters. But again, this was done in Denver, Colorado, a lot lower atmospheric pressure. You could make a barometer out of mercury, or you could also do it out of water. If you take a hose like this, put the water in a pool here, wiggle the hose back and forth, get all the air out of it so that nothing is in the hose except water, and then clamp the top and pull that hose out of the water. Water is going to be in that hose, and if we lift it high enough, the water is going to start to pull away from the top there. And we could calculate how high it is by knowing what the pressure is. This time we're using the density of water, and we want to figure out how high it is. And about 10.3 meters is the weight under 10.3 meters of water is the same as the weight under all this atmosphere. And if you had water that you're trying to pump out of the surface, remember there's no such thing as suction. You're not sucking the water to the surface. You're lowering the pressure and letting the atmosphere push this to the surface. So the best you could do with this pump is to get a zero pressure in there, and the best the atmosphere could do is push that up 10.3 meters. So these type of pumps are only for relatively shallow water. If we did that same experiment in the ocean, where we used salt water, which is a little more dense, and pull it up, same thing where we know the atmospheric pressure. This is just a little more dense than fresh water, and before it was 10.3 meters. In salt water, only about 10.1 meters. So going 10.1 meters deep here produces the same pressure as the atmosphere pushing down there. And that's 33 feet. 10.1 meters, same as 33 feet. And if you're familiar with scuba diving, or if you know anybody who scuba dives, that 33 feet is a magical number. That when we're at the surface of the water, when we're at the beach, we're already at 1 atmosphere. And if we go 33 feet deep, the weight of this much air equals the weight of this much water, so we're now at twice the pressure. And if you took a balloon from here down to here, well, the pressure is twice as much. Its volume is going to be half as much. Every 33 feet deep you go, you get to go 1 more atmosphere of pressure. So if you took a balloon from here and took it all the way down to about 165 feet, you're at 6 atmospheres. 6 times the pressure is going to be 1/6 the volume. And the reason scuba diving is so dangerous, if you were to go down 33 feet deep with scuba gear, and this was your lungs, and you breathed in a full breath of air, held that air, and went to the surface, well, you're decreasing the pressure by half as much. The volume's going to get to be twice as much, and literally your lungs can explode. Okay, and you do not want to do that. All right, so that's just a little bit about atmospheric pressure and how it is measured.